right, let's get started. Maggie, can you hear and see me all right?
Yes, I can.
All right. Hello, everyone. Last time we discussed ways that online and offline networks resemble each other and the ways that they do not. We talked a little bit about how influence might work online as well in particular. And we reviewed the genetic antecedents to, and to a lesser extent, the genetic consequences of social networks. We talked also about how an understanding of social networks might help bridge the gap between methodological individualism and methodological holism, two very fundamental ideas in the social sciences and also in this course. Today, we're going to be talking a little bit about what one might actually do with knowledge about networks. If you really understand human social networks, how might you be able to intervene in the world to make it better? How might, in other words, you exploit these social processes that I've been introducing you to? Now, there are at least three basic ways to intervene in a network. One involves connection. Here, the idea is that you could change the structure of social interactions. You might rewire the network. Who's connected to who, for example, arranging the ties between a group of individuals. The second idea is known as contagion. This involves changing the flows through a network. Given a fixed structure, given a fixed architecture of ties between people, who should you target, for example, if you want to maximize the spillovers? You want to maximize the spread of something spreading within the network. And a third possibility, so for example, to manipulate connection, you might, for example, examples of that might include like Weight Watchers, like introducing people who want to lose weight, or Alcoholics Anonymous. If you want to introduce people to each other who want to stop drinking, those are structural interventions. You broker ties that did not exist before between people, and that helps elicit some kind of new property in that group of individuals. Or the military squads example we discussed a while ago. And online, this is often possible, engineering these new connections. But typically, it's not so easy to do that in offline environments, to like force people to be friends with each other. Anyway, that's connection. Then I mentioned contagion, and the last is the notion of position, which is to manipulate the structural location of people within a network. And the simplest example of this might be you take a classroom and imagine that all the desks in the classroom have been nailed to the ground like a social network structure. You know, who's next to whom, for example, who's connected to whom. And now you have, let's say, 20 desks in the classroom and you have 20 students outside the classroom. And the teacher has to decide where to put those students in that network structure, in the desks in the classroom, in order to maximize learning in the classroom. You know, do you put the most able students in the front or the most able students in the rear? Or do you mix up the students, for example? And depending on how you arrange the students in the desks, you might elicit some new property within the group of individuals. I'm not going to be discussing position interventions in this class. I think that's the only mention of it I'm going to make. I'm primarily going to focus on connection and contagion interventions. And these interventions, all of them, can be done both online and offline. And after I introduce you to some of these examples, then I'm going to also be talking about how networks might be used not to introduce information into the system, but to extract information from the system, a different set of ideas. So we're talking about social network interventions, three kinds: connection, contagion, and position. We're only going to be talking about connection and contagion in this class. And when I'm done giving you some examples of that, I'm also going to talk a little bit about how these ideas might be exploited to extract information rather than introduce information into the graph. Now let's begin with a rather complicated experiment. This is, I think, an example taken from your readings, which involved manipulating connection, which, as I said, is much easier online than offline. So let's review this experiment. In this experiment, 128 people were taken and put into one graph, and a different 128 people were taken and put into another graph. And the scientists engineered the social structure in the network. Both of these networks had 128 people, everyone in this network is connected to 6 people, and everyone in this network is connected to 6 people. And everyone to whom everyone is connected in this network has 6 friends, and everyone to whom everyone is connected has 6 friends. So if I dropped you into these 2 networks, you could basically not tell the difference in which world you were in. How many people in your network? 128. How about you? 128. How many friends do you have? 6. How many friends do you have? 6. How many friends do all your friends have? They all have 6 friends. How many friends do all your friends have? They all have 6 friends. You could not tell the difference in which of these 2 worlds you are in, and yet we, with this bird's eye view, may have a different opinion about this. So imagine, for example, that the yellow dot here, every dot's a person, every line is a relationship. The yellow dot here gets infected with a germ. And in the next time step, can infect the 6 red dots to whom the yellow dot is connected. And in the time step after that, each of the red dots could in turn infect 6 of the white dots that they're connected to, and on through the network. In which of these 2 networks do you think that an epidemic of germs or of information would spread more easily? The network on the left, in which the ties are all randomly connected, or the network on the right, in which the ties are arranged in a so-called neighborhood configuration, where everyone is connected to the people nearby them in the graph. So I'm going to ask you the question. I want you to raise your hands so Maggie can get a quick sense of the class. How many people think a germ would spread more rapidly and more completely in random networks? Okay, and how many people think the network would spread more rapidly and more completely in neighborhood networks? So there's some variation, looks like. I don't know if you're raising or lowering your hands fast enough, but anyway, there's some variation in opinion on this. Let's see if we can kind of think it through a little bit. So for what would happen in this situation is that the germ would spread to these 6 people in the first time step and to their neighbors in the next time step, and pretty rapidly spread throughout the network. But over here, for it to happen, the germ would have to move slowly but surely. 1, 2, 3, 4, 5, 6, 7, 8 hops, let's say, to get to the other side of the network. Now imagine if instead I cut this little white connection between these 2 white dots and this little white connection between these 2 white dots, and without losing the total number of dots or the total number of connections, I rewired a shortcut across the middle of the network here. You should have the intuition that as the germ is spreading, bang, 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 as soon as it gets to this guy, bang, it'll hop across the middle of the network, and now an infection will start spreading from both sides of the network. And you should have the intuition that if you did lots of those rewirings through the middle of this network, you would eventually convert this neighborhood network into the random network. And this intuition is in fact why things like germs spread more easily in random networks than in neighborhood networks. Now, it used to be thought that everything spread better in random networks than neighborhood networks. But it turns out it's only things that spread by so-called simple contagion that spread better in random networks than neighborhood networks. Things that spread by complex contagion, it's the latter is the case. Neighborhood networks are better. And I can cultivate this intuition in you now by asking you to imagine that instead of a germ spreading or information spreading, it's something like a behavior, like smoking cessation. Imagine now that this yellow dot quits smoking and has some weak effect on these 6 red dots to quit smoking. But each of those red dots is surrounded by other smokers. So they really can't easily stop smoking because they're surrounded by other smokers. But here, these 6 red dots define a frontier in which each of them is connected to 2, 3, 4, 5, or 6 other people who have just quit smoking. So what happens in this situation, you get a wave of smoking cessation that spreads through the network. Things that spread by complex contagion that require reinforcement by the behavior of others, maybe because they're difficult to change behaviors and are not simple informational or pathological contagions, spread better in neighborhood networks than in random networks. So this raises the possibility that the amount of social reinforcement we give to people to improve their health habits may be more important then who is encouraging them to do so? In other words, a local community network of friends and neighbors may be much more important than some kind of celebrity broadcast mechanism that kind of starts an information cascade in the network. People care about what the real individuals around them are doing, and if they have multiple reinforcement, if several people are doing it, it may reinforce it. But most important, the most important abstract lesson from this experiment is that, for example, whether you are infected with a germ or whether you quit smoking may have more to do with the structure of the social network over which you have no control and about which you could know very little, if anything, than in your own individual choices and actions. In other words, we can engineer social networks with the same number of people and the same number of ties that give rise to very different properties. This is like the diamond and carbon example I gave a lecture or two ago. Same number of individuals, same number of connections, different organization gives rise to different properties in the social group. Now, my own lab has conducted other experiments to look at this over the last few years, evaluating how different topological regimes, different ways of organizing people affects the experience of the individuals within the group and the properties of the groups themselves. For example, in this experiment, we put people in a fixed network. So here is a network where there are 20 people and a certain number of connections, and those connections are pre-specified. People are dropped into the network and they are introduced to their friends. And they are given a little bit of money and told to play something known as a public goods game, where they're basically trying to cooperate with their friends. So the blue dots are the nice cooperative people, and the red dots are the mean defectors who take advantage, hope that their friends contribute to the common good, but they don't have to contribute. And in the beginning, about 2/3 of the people, about 60%, are blue dots, nice cooperative people, and they play multiple rounds of the experiment. And by the end, what you find is that pretty much everyone has shifted to a red dot and is a mean, non-cooperative defector, except for these little blue dots sort of in the corner of the network, keeping civilization alive, being nice to each other right on the boundary of the social group. So basically what happens here is it's like those high school science projects we all hated when you were assigned to a group of 4 people and you were the smart kid that did all the work, and they had 3 dummies that the teacher assigned to you to be with, and your choices were either to do all the work and then everyone would get an A because you did all the work, which didn't seem fair because they were defecting and taking advantage of you, or to say, if they're not going to work, I'm not going to work either, and then we'll all get an F, right? So what happens here is people are assigned to neighbors, their neighbors start taking advantage of them, and slowly they say, you know what, I'm going to stop being nice to my neighbors, they're taking advantage of me, and defection takes over the system, and by the end you have a ruined society where everyone is defecting. Now, in a different branch of the experiment, we experimentally manipulated the topological regime. That is to say, we experimentally manipulated the rules of social engagement. And here we allowed people, in addition to choosing whether to defect or cooperate at each round, we allowed them to rewire their network a little bit. We allowed a little of social fluidity. They could cut ties to other people, for example, defectors, and form ties to other people, for example, cooperators. And in this branch of the network, under a different set of rules of connection, cooperation persists in the social system. So I can take you people, you guys in this classroom, and I connect you one way, and you're mean and awful to each other. Or I take you sane people and connect you a different way, and you're sweet and kind to each other. The same human beings arranged in a different set of rules gives rise to different set of properties. Connection matters. This slide summarizes the results a bit more, and it shows that we had a number of experimental treatments. The green line is the fixed network that I told you about. And we also had this red line, this other control where the ties were rewired randomly. It's not so important right now. And then we had 2 levels of social rewiring, 2 levels of viscosity. We had the viscous dynamic situation in which we allowed rewiring, but not much, in yellow, and then cooperation disappeared from this system. And we also had a fluid dynamic situation where we allowed a lot more rewiring, and that's the blue example that I just told you. So the previous slide showed the fixed and the fluid dynamic situations were illustrated in the previous slide. And this shows the results across thousands of people or hundreds of people in multiple groups across multiple rounds are summarized here. Now, in a subsequent experiment, we explored the parameter space of the rewiring rate. On the x-axis is the rewiring rate. How much rewiring do we allow? Is it 0% rewiring? So it's a fixed network. You're stuck, no changes in ties. A little bit of rewiring, 5% of your ties get changed every time step. A little more, 10% of your ties get changed every time step, all the way up to 100%. That means every single time step, all of your friends are up for a change. Can form any connection you want and cut any connection you want. And on the y-axis is an estimated per round change in cooperation based on a regression model. Basically, it's how cooperative the groups are. And what you see here is you see a parabolic shape. If the network is fully rigid, people don't cooperate. And if it's fully fluid, people don't cooperate. Optimal cooperation is in the middle of the network where you have middling level rewiring rate. Now, the precise percentage is not what's important. What's important is the parabolic shape of this relationship. And the reason for this is that at very low rates of rewiring, people cannot detach from defectors. They're surrounded, let's say, by exploitative individuals, and their only choice is to become exploitative themselves. And so they resort to behavioral reciprocity. But at high rates, even if they detach from defectors, the defectors just reattach. As soon as I cut the ties to the jerks just reattach themselves to me. So we need an intermediate rate, optimizes cooperation. One example that I give to illustrate this principle is that many social institutions in our society are organized to move us to this middle rate. For example, consider the institution of marriage. We do not want to live in a society in which in which divorce is impossible. 0% rewiring, fixed marriage. If you're stuck to your spouse forever and can never separate from them, if your spouse is a jerk, your only choice is to become a jerk yourself, unless you want to be exploited for the rest of your life. Conversely, if it's very easy to get a divorce, and you can just say, I'm changing spouses every day, why would you invest in your spouse, or would they invest in you? There'd be no reason for you to be cooperative and nice. You again would be a defector. So you want a regime of divorce rules, an institution of marriage, which makes divorce difficult but not impossible. And that enhances the investment that each couple will make in the other member of the couple. So those are some examples of connection interventions. Let's imagine now contagion interventions. Totally different approach to exploiting an understanding of networks to influence contagion. So imagine now that you have two villages, or two schools, or two firms, or two colleges at Yale or something. And you map the network in the two elements, the two villages. And imagine that in this village, you pick 6 people at random, shown in the yellow dots, and you treat them with some educational intervention. You teach them something about breastfeeding, or anemia reduction, or latrine usage, or vaccination. You're trying to reduce vaccine hesitancy related to coronavirus, or mask wearing. You're trying to get people to wear their masks. And you teach these 6 individuals about mask wearing. Now, the ordinary perspective in this situation, and here in the control village, you don't teach anyone. Now, the ordinary perspective in public health is you teach these 6 individuals, and then you come back a year later and you see how many of the 6, did what you taught them. So maybe 3 of the 6 people took up the intervention. But that's not what I'm interested in. I'm not interested in response to treatment among the treated. I'm interested in response to treatment among the untreated. I want to know, what does everyone else in the village do when you teach them something? So for example, maybe 3 of the 6 people took up the mask wearing intervention, but they persuaded 3 of their friends to also wear masks, for a total of 6 people wearing masks in this village, compared to, let's say, 2 people by secular change in the control village. And that is the pure estimate of peer effects under control. But now you should have the intuition, maybe I don't need to pick the 6 people at random. Maybe instead of picking 6 people at random, I can pick 6 central people in the network. So maybe once again, I treat these 6 people. Of the 6 I treat, 3 of them respond, but now maybe they recruit 30 of their friends because of where they are located in the network. Same village, same intervention, same number of people treated, 10 times the effect, because I have now carefully and thoughtfully selected individuals, not based on who they are, but on where they are within the social network. These individuals, let's say, selected so as to be more central in the network, might be structurally influential. And we can experiment with various algorithms for picking these kinds of accelerating nodes. And this was discussed in the Valente reading or the Valente study in your readings. Or we could do something else. Imagine now that you have 6 people. Here you pick 6 people at random. And here you pick 6 people who are interconnected, who have high transitivity between them. And as I said before, maybe 3 of these 6 people respond. But maybe if they're interconnected, maybe 5 of the 6 people might respond here because they reinforce each other's adoption. In other words, using network methods might enhance the response to treatment among the untreated, as shown here. We get more response among the untreated, but using network methods might also enhance response to treatment among the treated. By carefully selecting who is connected to who, I might be able to jack up the likelihood that you will respond to whatever it is that I'm teaching you. Treating groups of interconnected people at once, for example, whole communities or subgroups within them, may increase the adoption of a particular practice among the people to whom that practice is given. Now, to really understand this, of course, we're going to need to do some experiments. In my laboratory, and actually Maggie has been involved in this too, and Ryan, if he's here today, has also been involved in this, have been doing experiments with this in various parts around the world, in India and Honduras and Uganda and so on. Let me see if I can explain to you the idea behind some of our experiments. Now, part of the problem is that everything I've discussed so far requires mapping the whole network to figure out who is structurally influential. And mapping a network is not always feasible. It could be expensive or impractical or maybe even unethical. And it's also not scalable. You can't figure out a way to exploit social contagion effects, but every time you want to do them, you got to map the whole network to do it. So the question is, how could we identify influential individuals without having to map network ties for a whole population? Now, it turns out that there's something known, or it's a mathematical fact about social networks known as the friendship paradox, that is summarized by the observation that your friends have more friends than you do. Did you know this? Your friends have more friends than you do. Actually, your sexual partners have more sexual partners than you do. And if you're a scientist, your co-authors have more co-authors than you do. This is a deep and fundamental mathematical property of human social networks, which relates in part, in a way I won't go into today, to the degree heterogeneity, the fact that people vary in how many connections they have. What this means is that the friends of randomly chosen people will have higher degree and be more central, and therefore possibly more capable of inducing spillover effects than the random people themselves. So imagine now we pick 6 dots at random, like before, and we now pick one of their friends at random. On average, their friends will be the orange dots, more central in the network. And I can cultivate this intuition in you by asking you to imagine for this network, if you picked anyone on the periphery of the network, any of these people, for example, this person, by necessity, this person's friends will have more friends than they do. This person has one friend. In fact, all these people on the periphery have one friend, but every one of their friends has more friends than they do. This person has two friends. So you should have the intuition that at least for people on the edge of the network, this principle holds. But it actually holds for everyone in the network. On average, your friends have more friends than you do. Or think about the idea of a popular party host who has 100 friends and is throwing a party. And all of their friends are wallflowers. They have like one friend, namely the party host. If all those 101 people came into a party, and then you pick those people at random, 100 out of those 101 people, if you ask them who is your friend, would say the party host. So for 100 out of the 101 people, their friend would have more friends than they do. It would only be if you happen to pick the party host that their friend would have fewer friends than they did. Same kind of intuition here. So the friendship paradox, mathematically what it says that is that if you count how many people have one friend, how many people have two friends, how many people have three friends and four friends. That's known as the degree distribution. Each of those is the degree of the node. I have one friend, that's degree 1. You have two friends, that's degree 2, and so on. If you look at the degree distribution, the average person has mu friends, which is the average of the degree distribution. But the average friend of the average person has mu plus the variance in the degree distribution divided by mu friends. The average person has the average number of friends, but the average friend of the average person has some higher number of friends. So what this means is that you can actually identify these orange nodes without having to map the network. It's miraculous. It's so cute. You just go into a village or a classroom, you pick people at random, you have them nominate their friends, and you deliver the intervention to the friends of the original people, not the original people. And those friends will have more structural power. And now you've identified them without the expense, headache, or potential ethical problems of mapping the whole social network. And we've been conducting field trials about this using public health and other interventions in various settings. In Honduras, we've done experiments with vitamins, water purification, and neonatal care. In Uganda, with HIV treatment. In India, with anemia treatment. Online, we've experimented with cooperation and information cascades. And in physician networks, we've looked at prescribing and safety practices among doctors. Let me show you a few of the results just to give you a feel for what can be achieved with these ideas. This is a place where we work in the highlands of Honduras. This is a very poor part of the world. People here live on less than $2 a day. It's a coffee growing region. These are small little villages, as you can see, in the very hilly part of the country. And this is one of the first projects we did. We had 32 villages that were located near La Union, which is a small town in sort of central Honduras. And we mapped the networks of all the villages. And notice that there were not many connections between the villages. This is the network of this village and the network of this village and the network of this village. And then we randomly assigned the villages to one of 3 different network targeting algorithms. In 1/3 of the villages, 5% of the people were chosen at random. In another 1/3 of the villages, 5% of the people were chosen who had the most connections, the highest degree. And in another 1/3 of the villages, 5% of the people were chosen at random, and then we took one step away from them to their friends using the friendship paradox or the friendship nomination technique and delivered the intervention to that 5% of people. And the question is, how do we move a whole village and not just individuals to change their behavior? Given a budget constraint, given only a certain amount of money to reach a certain number of people, who do we target? Who, in fact, can create the most externalities for behavior change, and how can we exploit this? Here's one of my former undergraduates. This is from when we did this original project like 10 years ago, and she's in the field trying to deliver the intervention. And this slide illustrates how this might work in practice. This is the network of one village. And here is what I show you is if you pick 5% of the people at random, you would get the orange dots. But if you pick the 5% who had the most connections, you would get the yellow dots. So you should have the intuition, oh goodness, the 5% of people that have more connections are more central in the network. They, if we get them to change their behavior, they might have more impact than the 5% random chosen. In the limit, look at this poor person. They're connected to this person who's connected to this person. Even if you persuade this person to change their behavior, it's not going to have much effect. They can only influence 2 other people, let's say. And here is one of my former graduate students delivering the intervention. It was a clean water and a multivitamin intervention. And here's a slide of our results for those 2 interventions. Here on the y-axis, we show the proportion adopting multivitamins. And on the x-axis, we show the proportion adopting the chlorine clean water intervention. And on the x-axis is the days since we targeted them. And then there are the 3 different targeting algorithms. And what we find is that, at least in the case of the multivitamin intervention, the friendship nomination technique outperforms the other techniques. And we speculate that the reason the intervention failed in the chlorine intervention is that the chlorine intervention required complex contagion. It required multiple reinforcement from other individuals, whereas the multivitamin intervention was more like an informational cascade and easier to adopt practice. And we can actually visualize these cascades and how they differ here. So here is a village with random targeting. So we target 1, 2, 3, 4, 5 people. And then this person spreads the intervention to this person, but then this person, it extinguishes, doesn't spread to anyone else. And this person spreads the intervention on day 2 to this person, and then this person spreads it to those other people, and then it extinguishes. And so you can see that there are many more dead ends in random targeting, and many fewer people overall adopt than in nomination targeting, where here, this person influences all 4 of these people at different days, who in turn go on to influence more people. So you can literally trace out these cascades and visualize them. And I think actually, I can't remember, Maggie, did I assign the Lancet paper for reading, or am I just presenting it in class?
I can check.
I can't remember. Did anyone, was this image in the Lancet paper that I assigned, or did I not assign it? I can't remember right now. If you guys, if Maggie tells me this is on the syllabus and not a single one of you recognizes this image, I mean, I can be forgiven my forgetfulness, but you guys should be doing the reading before lecture. So we're about to hear
the Kim social network targeting article was in there, but it doesn't look like this one was.
Okay, so in fact, everyone, you were all assigned this paper and it has this image in different colors in the paper. So every one of you should have recognized this image and said, oh yes, I recognize that image. I can explain it to you. You need to do the reading before lecture, people. Anyway, all right. Now in a follow-up project, we now have expanded this work to do an enormous randomized controlled trial of a maternal and child health intervention in a different region of Honduras with 176 villages and 30,000 people. And what we're doing here is we are experimentally varying the dosage of people chosen to get the intervention. It's a 2-year educational intervention related to maternal and child health, and whether or not the people are chosen according to random targeting or friendship targeting. And this is what we expect to happen. So 176 villages, 30,000 people. There's an 8x2 factorial design, 8 percentages, and 2 targeting methods. And there are 11 villages in each of those 16 cells. And what we set out to show, and what we have shown, is that if you put on the x-axis the percent targeted from 0 to 100%, that's the number of people you choose to target in each village. And on the y-axis, the percent reached, how many people adopt the practice. If there was a linear response, there was no social effect, if you targeted 100%, maybe 50% would respond. In other words, you can't always persuade everybody. And linearly, if you targeted 60%, maybe 30% would respond. But you should all know that's not, of course, what happens. There are these S-shaped diffusion of innovation curves. At the beginning, at low percentages, people don't adopt the practice because their friends haven't adopted. Like if I try to get you to wear a new fashion, you might not adopt that fashion until you see a few of your friends adopting the fashion. So initially, the social effect works against you, suppressing adoption until you reach a critical threshold. And then you have explosive adoption, explosive growth, until you plateau. And now the social effect, which previously worked against you, now works for you. And then you plateau at 50%. Our question was, could we get an enhanced social effect by using friendship nomination? So now, maybe if we pick 20% of the people using the social network targeting strategy, it might be as effective as if we had picked 80% of the people using a random targeting strategy. Do people understand where I'm at? And this, in fact, is exactly what we've observed. These are unpublished preliminary results that look at one particular outcome related to taking care of the umbilical cord in babies, and show that with friendship nomination, we can shift adoption to the left. So we can exploit these ideas to enhance the response of behavioral interventions, both among the untreated and among the treated. We can use it to deliberately create spillovers by leading to cascades, or we can use it to deliberately exploit peer reinforcement so that you're more likely to respond if I also treat your friends. And in fact, we can quadruple the return on investment in some settings. Taking into account the network effects of our interventions might actually modify our cost effectiveness interventions. So we're trying to figure out, should I do this seatbelt use intervention in a school, or this smoking cessation intervention? I'm going to treat 10 kids and 3 of them will stop smoking. That's great. I spent $1,000, I got 3 kids to quit. That's $300 per kid. But what if the 3 kids who quit influence 10 of their friends to also quit? Now the same $1,000 means 13 kids quit. So that's $70 per quitter rather than $300 per quitter. The cost effectiveness, you see, will now be seen to be changed when we take these interpersonal effects into account. So people are connected, and therefore their health and behaviors are connected. Now, one thing that is common and interesting about social network phenomena is that they are nonlinear, and they can manifest so-called phase transition type behavior, this inflection point that I alluded to earlier. Things do not change smoothly. Some of you may have seen this viral video that I'm about to show you, but others probably have not. Quick, raise your hands if you've seen this video before. This is the Sasquatch Music Festival in 2009. Just a few of you, good. So most of you have not seen this video before. I want you to watch what happens, and then I'm going to ask you a couple of questions. Here we go. And you should be able to hear the sound. Maggie, tell me if you don't hear anything. Oops. Okay, who wants to tell me what happened there? What were key things? Yes, Kenneth, some observations.
Yeah, so I noticed it took like the time it took for the second and third people to join that first person, that time interval, those two time intervals were about the same, but then thereafter it really started picking up, and then as more people joined, it hit this sort of critical mass point, and then that's where the crowd really started growing.
Exactly. Very good observation. Other observations. There's a lot going on in that video. Any other ideas? Yes, Severin.
I think one of the other things that I noticed was that at first it seemed as people were kind of like looking around, and I mean, you can't say for sure what they were thinking, but definitely appeared as though they were like silently judging this person who's like up there, when it was just one, but definitely like as there was a larger and larger crowd.
I was
like,
judging him for sure. I was judging him for sure. I was like, oh my God, this guy's making an embarrassment of himself. But he really stuck to it, right? Anyway, go on. Yeah, so other people are probably doing the same assessment.
Then kind of like as you go like longer and longer through it, you definitely see that like the energy surrounding the group changes, not just like the dynamics of the group.
Yes, very good. Other observations. Did anyone else observe anything else? There's a lot going on in that video. There are more. If you observe something, you probably noticed it correctly. Did anyone observe anything about the, yes, someone else raise their hand. Was it Kenneth or no, Chloe? Chloe, what do you think? Yeah.
Yeah, I mentioned in the chat, but like this kind of remind me of like the protests that happened at Harvard Yale game 2019. Like at first there was only like a few students like coming out of the field to protest, but then it took a few minutes for students to like make a whole crowd, both from Harvard side and Yale side, and it was, yeah, it reminded me.
Yeah, okay, so very good. So that there are other examples of this. That's right. And in fact, there are other examples of this all the time, right? In social phenomena, in fashions, in adoption of products, in protest movements. A lot of people just join because they want in on the fun. They don't even necessarily believe in what's happening. Other observations. Jennifer.
Yeah, so it seemed like at first, or like the first couple people that came, it seemed like some people came with like another friend and dragged another friend with them. But as the group got larger and larger, it just looked like streams of people just kind of came in. So it didn't matter if they were connected to other people who were in that group and dancing. It just like because they saw something happening, they wanted to join rather than going because their friend was going.
Very good. Yes, there was a sense. I wouldn't say that was the beginning 4 or 5 people. Those were solitary individuals. But then there was a phase in which you had couplets that were coming, and then you had all these individuals coming down. Anything else? Ayman.
I think at the beginning it was very clear that they came there to dance, and then at the end of it, the like activity just evolved into like a mass of people just jumping.
I think that's also very likely true, and that relates to the point I made a moment ago, is some people join out of solidarity rather than conviction. It's not that they want to dance, it's they want to be part of whatever it is that's happening. Did anyone notice anything about the gender of the people? What was happening with the men and women in the group? Did anyone notice anything about that? How many of the first 10 people were women?
None.
None. Okay, so attributes of the individuals are also very important. So initially you have solitary men going up. And as one of you highlighted, often what's most important in these cascades is not the act of the first individual, but the act of the second. The second person to join is actually more important often in the maintenance of a contagion than the ignition, than the first person. And the same applies to the subgroups defined by gender. So in other words, you have all these men joining, and finally one woman says, okay, there are enough guys up there that wouldn't be creepy. Like if there's one guy and I went up and started dancing, he might misinterpret what's going on, but now there are 10 guys I can join. And as soon as one woman joins, then more and more women say, okay, it's okay to join, and they also join. You can have parallel cascades here defined by gender. So if I can now recover where I am at, let's see if I can operate this damn, I wish I were in a classroom with you guys. I wish it so much. Stop thing, and then presenter view. Okay, can you see that S-shaped curve? Is that visible to you? Yeah. So this is the unsexy way of showing you what I just showed you, okay? Much less vivid form. As more people adopt a behavior or an idea or a product, my pointer is gone, but you can imagine what's going on. Then you begin to have, it changes the propensity of others to adopt. And this property, the fact that as more people adopt, it changes the threshold of subsequent adopters, plus the finite size of the population, gives rise to this classic S-shaped epidemic or diffusion of innovation curve. And initially, a small fraction of the population, the early adopters, adopt, and then more and more do, until at the peak of the epidemic, the percentage affected grows rapidly until a new plateau is reached and fewer susceptible people remain. Now, let me just see where I'm at now. Let me just see first of all, there we go. Annotate, spotlight thing. Okay. Now, more recent work in our laboratory has shown that information might be extracted from networks rather than just delivered into them, which can provide a whole new way to predict epidemics well before they strike the general population. And a month ago, when I did the COVID lectures, I spoke to you a little bit about these ideas. I'm going to revisit them now in the setting of this app that we had released that relies on these insights in order to forecast your risk or your loved one's risk of encountering the coronavirus. So remember last time what we said about the variation in network position. We said, for example, that different nodes have different positions within networks. One way you can quantify that is by the degree. This node has 4 connections, this node has 6 connections. Both of these nodes have 6 connections, but this node has a special property. It's more central in the network. This node here it has the same number of connections as D, but D is peripheral and C is central because C's friends in turn have more friends themselves. So you had the intuition that if you could, that if something started at random in the network, a contagion began stochastically in the graph, someone was infected with a piece of information or a germ, you had the intuition that it was better to be D than C, because anything spreading in the network is going to reach C sooner than it reaches D. And in fact, C is going to be more likely to be infected or affected than D is by the end of the epidemic. So you all had the intuition that C is going to be more likely to get whatever's spreading through the network than D, okay? So for example, if a germ is spreading, it's better to be D than C, but if a juicy piece of gossip is spreading, it's better to be C than D, right? C is going to be more likely to get it. But what this means is that if we could figure out a way to identify C's and follow them, we might be able to build an early warning system to forecast the course of epidemics. So for example, if we could monitor 6 central people in the network, whether it was, and we were trying to monitor, okay, what do you think about mask wearing? Have you been infected with COVID? We would be able to set these individuals up as sensors, and these individuals would be more likely to get whatever's spreading. If we saw them contract a germ or a piece of information, we would know that soon the rest of the network would also be affected by whatever it was. And that these 6 central people would be better than 6 randomly chosen people in the network that ignored social network information. This is how polls are ordinarily conducted, shown on this slide. You have a population, you pick some people at random, and you survey them to see what's happening. And that is like, gives you a sense of what's happening today. But that's not what I'm interested in. I'm not interested in knowing what's happening today. I'm interested in knowing what's going to happen tomorrow. Can we identify central people, track them, and if the contagion spikes in them, we know that soon the rest of the network is going to be affected. In fact, what we would theorize is the following theoretical differences in epidemic curves. This shows the cumulative incidence of the contagion, just like I've been showing you. In the dotted red line shows the population in general, but among central people, the curve should be shifted to the left. In fact, if you now look at the daily incidence of the contagion on the y-axis, and again, time on the x-axis, the epidemic should peak some amount of time delta t sooner in central people than in randomly chosen people. So what this means is that we could get advance warning, not just rapid detection. It means that if we could pick a population of people and monitor them and their friends, just again like in the friendship paradox, we should find that the network should, the epidemic should spike in the orange dots before the yellow dots. Now, we tested this idea using an outbreak of H1N1 flu among Harvard College students. This is when I was still at Harvard, between September and December of 2009. We drew a random sample of 1,300 Harvard undergraduates, and we asked them to nominate their friends. And we followed all of these people, the random people and their friends, for flu-like symptoms on a daily basis for 120 days in 2009. And we did this by passively observing whether they went to university health services with their permission, and by, in those days, we didn't have web surveys, so we had to text them twice a week and say, in the last 3 days, have you had a flu symptoms or not? And they would text us back, and we would automate the procedure of collecting these data. So here again are the theoretical predictions. Our predictions are that the epidemic will spike in the friends before it spikes in the randoms. This is the theory, and this is what we observed. Exactly what we predicted. So what we found is that the curves, this is the days since September 1st, 120 days. This shows the cumulative incidence of influenza. We found that the curves, that the friendship group diverged from the random group, I don't know, 60 days or something, 2 months before, 46 days. The earliest warning came 46 days before the peak of the epidemic. And in fact, the epidemic was 14 days sooner in the friends of random people than in the random people themselves. This, in other words, this is the obverse of the Honduras experiment I showed you before. Instead of injecting information into the system, we use these insights to extract information from the system to build an early warning system for epidemic outbreaks. And now, as it turns out, of course, we could map the whole Harvard network. In this particular case, it's not necessary that we mapped it, but we could map it. And this is the largest, this is a component of 714 people here on September the 1st. Each line represents a friendship nomination, and each node is a person. In a moment, I'm going to take daily cuts through this network for 120 days. Infected individuals are going to be colored red. Friends of infected individuals are going to be colored yellow. And the node size is going to be proportional to the number of friends of yours that are infected. And what you're going to see is you're going to see the epidemic bloom in the network around people who are more central within the network. Here we are now, September 19th, 20th. The epidemic begins. It's flushing and spreading contiguously within the graph. People are being recruited. And you can see that the periphery of the network lights up later than the central part of the network. And now that we reach the end of our follow-up period. And since we actually had the whole network, we could actually assess the relevance of various network parameters even without the friendship method, as we predicted. And we found that actually, if you partitioned the network to have high in-degree people, if you monitored high in-degree people, you would have 8 days of early warning, or high centrality people, you would have 4 days of early warning. And actually low transitivity people, people whose friends were not friends with each other, have a lot of extra warning. The reason here is that if your friends are friends with each other, you have a little insular group. But if your friends are not friends with each other, your friend's friend reaches further into the network, exposing you to more pathogens. So little insular groups are less likely to get infected, but of course, if they do get infected, they infect everyone within their group. Anyway, this is all discussed in the paper. Some of these details are not so important. The general principle is what's important. Now, how much advance warning? Here I've just shown you that for influenza and college students, we could get 2 weeks advance warning, but how much advance warning you get depends on a host of factors. It's not always 2 weeks. It depends on the intrinsic properties of the thing that's spreading. It depends on how you ascertain that an infection has taken place. It depends on the nature of the population. It depends on the structure of the network. And it also depends on what I call network deformation. It depends on whether the thing that's spreading changes the network as it spreads. For example, if something like Ebola is spreading and it kills the victims, as the victims die, network ties are lost. So the network structure is changing as the thing is spreading through the network. And as I've been suggesting, this method is not restricted to germs, but actually works with respect to anything that spreads in populations by person-to-person means, including a variety of phenomena related to, including pathogens, information cascades, norms, and behaviors, okay? Anything that spreads in networks, you can use the friendship paradox method to identify central people, and if you can monitor those people, you can forecast the course of the epidemic. But the key thing is that for this method to be useful is that the thing in question must spread interpersonally, at least in part, and not just affect people independently, for example, via a broadcast mechanism. You know, if Oprah is broadcasting her favorite book and everyone hears about it from Oprah, that's different than rumors spreading through the network. A broadcast mechanism, it doesn't matter whether you're central or peripheral, you're going to hear Oprah. But a person-to-person spreading mechanism, it matters whether you're central or not. Similarly, something like malaria that spreads by infection from mosquitoes, the mosquitoes rain from the heavens and can infect anyone in the network. It's not the same as something like syphilis or the flu, which spreads from person to person. This method would not work for malaria, but would work for syphilis or the flu. Now, we tested this idea as well in a subsequent project on Twitter, where we looked at 200 hashtags. We picked 50,000 people at random from Twitter, and then took one step away to one of the accounts that they were following. So we had 50,000 randoms and 50,000 group censors chosen by the nomination method. And we had 200 hashtags like Light Up Nigeria. And here we tracked the growth of the Light Up Nigeria hashtag among the 50,000 randomly chosen people, and among the 50,000 censors, Light Up Nigeria shifted to the left, peaked earlier in the friends of random people than in the people themselves. And across 200 hashtags, on average, we knew 7 days in advance what was going to be popular on Twitter by monitoring the friends of randomly chosen people rather than randomly chosen people themselves. Is that clear? Now, the availability of online and other data about human behavior heralds the onset of a new kind of computational social science that enhances understanding of social processes and that also facilitates interventions of the kind we have been talking about. When I was your age, social scientists fantasized about having a kind of power. Like they would say, you know, if we could only have like a little Black Hawk helicopter, a microscopic one, and it could fly on top of you and monitor where you are and who you're talking to and what you're buying and what you're interested in. And if it could do this for a whole city of people in real time, that would be incredible. This is what the data that social scientists fantasized about having just 20 years ago. And of course, as you all realize, that's exactly what we have now. Each of you has a little Black Hawk helicopter in your pocket that monitors where you are, who you're talking to, what you're buying, what you're interested in, and so on. And the availability of this kind of data is exploding in the form of internet data from social networks and websites, telephony data. I introduced you to some of the telephony data we use to track the epidemic in China earlier in the course. Video cameras in cities that are coming increasingly online. RFID devices, little tiny devices, pretty soon will be in every product that track that product. Administrative records like physician visits and crimes, transaction records, geographic information, voluntary losses of anonymity. For example, people sharing their DNA online, for example, or other stuff online. Many of you guys are part of this sharing generation. You share all this stuff online that your parents and I are thinking, what are you doing? But you think it's normal to do this. Or personal genomics. These kind of data are exploding and are going to continue to do so for the foreseeable future. We are in an era of massive passive data, and we will increasingly be in a situation to obtain passive surveillance in real time. But the question remains, what are the big intellectual questions that such data might be put in the service of? I mean, and moreover, what can we do with these data to make the world better? In terms of the questions, I think there are several deep and fundamental questions. For example, what are the origins of behaviors and values and norms? In economics, they often take this for granted. They say, imagine that people have tastes. We have no idea where those tastes came from. We don't care. But if they have tastes, then let's model how they shop and their utility and their behavior, conditional on tastes. Sociologists are much more interested in the origins of these tastes. Why do people want what they want? Often people want what they want because of their friends, what their friends want. And so having data on these types of things can give us new ways of understanding the deep origins of behaviors and values and norms, and the origins of social structure and of collective action. If we're going to understand emergence, how properties emerge in groups that are not within groups themselves, if we're going to understand methodological holism, if we're really going to understand groups as a whole and their emergent properties, these kind of data can help. We can understand the supra-individual, institutional, and structural constraints on individual action. We can understand structure much better and not just agency when we have access to such data. Now, more careful and more complete observation are great, but in the service of what? Will this data collection, in its breadth and detail, prove to be like the data that Tycho Brahe analyzed, that Tycho Brahe collected, and that Johannes Kepler analyzed? Or will these data instead be a distracting profusion of noise? Many of you will know the story of Tycho Brahe and Johannes Kepler, but some of you won't. And the story was that Tycho collected these data about the stars, and then eventually Kepler was able to use them to understand the heliocentric structure of our solar system. Tycho was onto something. In 1563, at the age of 17, he wrote the following: I've studied all available charts of the planets and stars, and none of them match the others. There are just as many measurements and methods as there are astronomers, and all of them disagree. What's needed is a long-term project with the aim of mapping the heavens, conducted from a single location over a period of several years. That's exactly what we have now in the social sciences. With this science, we can understand how exactly the whole comes to be greater than the sum of its parts. And we can use many of these insights, in my judgment, to improve society. Okay, I have a few minutes for questions. Any questions? Yes, Iman.
I had a question and I'm not sure how to phrase it, but I'm thinking the idea is that behind the friendship paradox and how your friends have more friends than you, if the shouldn't is the idea of the friendship paradox recursive? Does that mean that the friends of your friends have more friends than your friends? And
Yes.
if so, is that behavior reflected in the patterns that you were mentioning just 5 minutes ago like what I'm thinking of is that S-shaped graph and how friends have the S shape before them. Would those friends have the S shapes before those S
Yes. Yes, Iman, that's terrific. It would be friends would be shifted even further to the left. And if you think about it just a little bit, one of the things you would want to do to optimize that strategy would be to restrict to there being no backward stepping. In other words, I nominate my friend, and then we say to my friend, okay, you nominate someone, but we prohibit my friend from nominating me back. Otherwise, you just come back to me. If you force onward nomination, then you even enhance the little intuition you have. But the step from the second to the third friend is in fact shorter. The distance, the delta t shifted to the left, is smaller than the delta t from the first step. So in fact, you don't gain as much from the second step as you do from the first. Now, there are other ways to enhance this whole friendship paradox trick. For example, instead of asking me to nominate a friend or picking one of my friends at random, you ask me, of your friends, who do you know to be the most popular friend? So the heuristic now is not, for example, you said, Nicholas, if ego's friend is a good way of increasing structural influence, what about ego's friend's friend? And you're right, but there are other ideas like ego's most popular friend might be a good way to enhance the bang in this situation. Other questions or thoughts? Yes, Maria.
Yeah, I may have misinterpreted this, but in the unpublished graph of like S-shaped curves, I think I recalled that at high rates of like targeting people, the curve for the like friends of randomly chosen people dip below the
Yes.
the curve of randomly chosen people. So I was just wondering if there was any intuitive explanation.
Yes, very good observation. Let me just bring that up. This slide, right? So there are two things going on. Can you see it? Is it on the screen? Okay, so two things going on here. You're saying, look, Nicholas, this is below that. First of all, this is sampling error. In other words, it's just when you fit, all the data points aren't here. When you do statistical fitting of the curve, this is like noise. Like this might be statistically indistinguishable, these two curves, or even this might in truth be above that. But when you fit the curve, you get this property. So that's one possibility. And in fact, that's what happened here. But there's another subtle possibility that you are onto, which is it may be the case that friendship nomination accelerates adoption, but it might or might not increase total adoption. In other words, you might expect the friendship nomination curve to reach the same ultimate level as this, surpass it, or be below it. That's a different set of ideas than whether it shifts the curve to the left. Do you understand?
Mm-hmm. Yeah,
Very
that
good.
makes sense. Thank you.
Any other questions? Aren't networks really cool? It's really cool, isn't it? I got addicted. Like once I started studying networks 20 years ago, I haven't stopped. Like you never stop once you start. Yes, David.
Is it even like ethical in the field to like say like, oh, I'm gonna give an intervention to your popular friend and not to you?
Yes.
Not even.
Excellent question. We have the same concern. So you go into a village and you say, okay, I picked 10 of you at random. Who are your friends? Thank you very much. I'm going to go give this intervention to your friend and not to you. And this struck us as infeasible. So we just completed another trial that I didn't show you about, in which we do pair targeting. We, instead of picking 10% of the people at random and then going to their friends, which would be 10% chosen by friendship nomination, we pick 5% of the people at random, and then we 5% of the people at random, and then we go to their friends for a total of 10%. Could you excuse me for 1 second? Excuse me 1 second. No, I don't think we want any oil because we're trying to empty the tank because we're replacing with propane. Yeah. Oh, this is propane now. For where? Oh, for that tank. Thank you. Sorry, household problem. Yes, David, did I answer your question?
Yeah, thanks.
Any other questions before I let you go? Thank you all. See you next week.
Thank you.
You're welcome.
Thank you.
Yeah.